This video goes over the topic of multicast receivers and how they actually signal their interest in multicast streams. Now, throughout our lectures, we have always made one important distinction between replicated unicast broadcast versus multicast. We have always indicated that multicast actually has a lot of control. So multicast receivers have a lot of control in signaling the interested groups. And that is what distinguishes multicast from broadcast. This whole concept of only sending traffic to receivers that are interested in that traffic. Well, that information has to originate somewhere. Somehow the receiver, once it knows which group it's actually interested in, it has to indicate to the multicast network, so at least the very first router, on which groups those actually are, or which groups would you like to receive. That is the job of IGMP, which we will be discussing here. But that is the overarching concept for this particular lecture. So let's get into this. Now, if you think about multicast flows within a VLAN, so we are not even leaving a VLAN. Everybody, all of the multicast sources, the multicast receivers, they are essentially just connected over layer 2. So they are connected to a switch and they can opt for each other and they're connected at layer 2. They can send layer 2 frames to each other. In this particular case, even IP multicast becomes mostly automatic. Whether it's done on a very on a broad basis or on a specific basis, that differs from switch to switch. But it's mostly automatic, so the sources can send the traffic and the receivers are almost guaranteed to receive that traffic, that multicast stream. Now, there is going to be a difference between how basic switches, so less advanced switches or legacy switches or consumer level switches handle this multicast versus how multicast aware switches handle it. Basic switches essentially treat multicast just as broadcast. So once they receive a multicast packet, they don't bother looking at the actual group contained in the packet or the source contained in the packet. They burst it out of all of the ports within that VLAN except the ingress port. If you think about it, that is the very definition of broadcast. So it's no different than how you would have broadcast traffic being sent on a switch. So sent out to all of the ports except the port where you receive that traffic. The good part about this is this automatic part. So yes, it facilitates the automatic part of within a VLAN multicast. But the con of this is all of the hosts, so same con as it would be for broadcast, all of the hosts on the VLAN will then receive the stream. There is no concept of interested receivers. What happens once the traffic gets to the actual destinations or the actual host, the interested receivers will accept these packets because obviously they're tuned to that multicast groups. The other receivers will just drop the traffic. Obviously, it's not very efficient. Obviously, it doesn't scale very well, but it works. Now, there can be multicast aware switches. Now, these are switches that actually inspect the multicast signaling. So think of like a firewall. So as the receivers are signaling the routers, the switches are sitting between the receivers and the routers, and they inspect this multicast signaling. And what they can do, what the signaling is the rest of the lecture. So I don't want to get ahead of myself, but there is this information contained in that signaling. Once the switches inspect that signaling, they can now create a proper multicast source, and they can create this proper multicast state. And they can create this multicast state for every switch port. So for every switch port now they know which multicast groups is the host connected to the switch port interested in. And now it can forward the multicast traffic. So once the multicast traffic starts coming in, it can inspect the group in that multicast traffic, the destination IP, and it can forward it to only the interested receivers. We will go into this in a lot more detail this topic itself is called IGMP snooping, and you'll find it in a later lecture. But for right now, just know that some switches are not aware of multicast, and there are other switches that are aware of multicast. That brings us to IGMP, or the Internet Group Management Protocol. Now, this is a very simple protocol, but it essentially provides all of the power of IP multicast on the receiver side. Getting into this. Now, first the receiver has to know which multicast group to receive. So the receiver, the IP stack on the receiver, or the TCP IP stack on the receiving host has to know which multicast group to receive. Once it knows that multicast group, so once it knows which group it actually is interested in, it has to inform then a local multicast enabled router. So multicast enabled router is any router on the subnet that actually understands multicast, that actually runs a multicast routing protocol, that does all of the fancy things that we talked about in a previous lecture, the multicast router lecture. So this is a multicast router. The receiver, where does it acquire this information? Usually this information for the receiver will come from the application layer. So some application is running, maybe it's a video feed application that is looking for cameras on the subnet. Maybe it's a financial application that is looking for some quotes that are being multicasted over. Maybe it's a video conferencing thing. It could be a whole host of things, but ultimately this information for the most part comes from the application layer. The router itself, the terminology is important here. So the terminology is going to be used over and over and over again. So it's very important that you actually get used to that terminology now. This multicast enabled router that we talked about, this is also called the last hop router. And actually you will see me use the words or the acronym LHR throughout our courses. It is that important. It's one of the more important routers in a multicast network, because that's where the receiving signaling, the receiver signaling is actually beginning. And like I said, it's on the same subnet, so it is reachable at layer 2. You have a direct connection to it. This particular step, where the receiver now knows about the multicast group and it has informed a multicast router, this is what separates multicast from broadcast. So this is one of those important things where now the joining of the group is explicit versus what it used to be, which was implicit. Send the packets out and then the interested receiver will receive them, everybody else will sort of drop them, but it was implicit. The router was just assuming that everybody wants that group. Now the router has been informed by the actual receiving host, and the join is much more explicit. So the receiver, what does it send? How does the signaling actually work? It works in something called IGMP. So again, Internet Group Management Protocol. For the people who like trivia, it's protocol number 2, ICMP being protocol number 1. So it's IP protocol number 2. We are going to discuss it throughout this lecture and probably one more lecture. There are so many different versions and there's so many different details to go over. But for now, I'll suffice it to say that it is an IGMP message that is sent that indicates the interest to join a group. Now the multicast router on the segment, it is listening for all of these IGMP messages. So it is sort of tuned to all of those ICMP messages. Once it receives a relevant I said ICMP, I meant to say IGMP. Now once it receives a relevant IGMP message, and that IGMP message contains the interested group for the particular receiver, it will obviously receive it on an interface. I'm not trying to be facetious here, but that is what is happening, right? It is receiving that message on a particular interface. What happens now is you have an IGMP message. That IGMP message has identified an actual G or a group. So the interface now can be added to the OIL or the outgoing interface list. Now, this is not IGMP, right? So this is the multicast routing protocol that we will talk about later. But if you think back to our lecture, that oil, every router needed an oil to create a tree. So there was an IIF, there was an oil. This is the beginnings of that multicast tree via the very first oil. This is going to be the very first oil that is going to be in your network. Now, this IGMP signaling can be turned into multicast routing protocol signaling, and you can carry this information further into your multicast core. But this is the beginning of that whole multicast tree. So going a little bit more into it, now don't worry about the output just yet. I'll go over the relevant parts right now. But what you have to realize is the part in orange. So the part in orange right here, this part, that table, that is the multicast routing table. If you go back to one of our beginning lectures, the basic lectures, this is something that you've already seen there. This has those incoming interfaces. This has the outgoing interface list. And what I am trying to show you here is this router, obviously, if you look at it, it is connected to a segment. So this router becomes the LHR. Now on this LHR, there are incoming interfaces and there are outgoing interfaces. What I am trying to show here, again, don't get lost in the details just yet. The intent to show here is where is this information coming from? Where is this gigabit Ethernet 01 coming from? For all of these groups. So there are groups and there are oils for those groups. So again, looking at the groups, here's a group, there's another one, another group, and two more. So all of those groups have oils. And what I'm trying to show here is where is that information coming from? That information could have come from any one of these receivers down here. So you see a bunch of receivers. There are, well, theoretically 4 receivers shown on this diagram, but scale it out and it could be many different receivers who are all connected to a last hop router. So they will all send IGMP messages to this last hop router. These IGMP messages may have some groups attached to them. And those groups, so in those IGMP messages, those groups then create a state on the last hop router. That state would be received on particular interfaces. So in this case, it's just a single interface. So assume that this is G01 because that's the only interface I have. So all of the IGMP messages for these groups have been received on these interfaces. And if you think about it, they've been received by different receivers. And how do you know? Or they've been sent by different receivers. They were received from different receivers. And how would I know that? I would know that because of this field here. So this tells you where that message originated from. But ultimately, what is important here is that we take each one of these pairs and we create a state in this table here. So if you look at it, look at the very first state. It is 239.123. So that very first state in the multicast routing table is 239.123. And the very first state in the IGMP table is 239.123. The next state is 239.122. Same state reflects itself on the multicast routing table. So ultimately, we have taken all of the information that was received from my end receivers, the actual receivers who want to receive that traffic. I populated this table here, and then the router took all of that information and converted into information that is basically populates the multicast routing table. And it will also be turned into that multicast routing protocol information and sent towards the multicast core. Again, do not get lost in the weeds here. All we are trying to show here is this is the beginning of that boundary between the receivers and the multicast routing protocol. This is the very first thing that happens that actually populates the multicast routing table and also gives it information to talk to the other peers across the multicast core. Now it's time for the actual details of the receiver signaling. So far we have just called it multicast messages. Now we actually call it number one signaling, and I actually get to tell you what those specifics entail, what those messages really are, and how basically this whole infrastructure comes into being. So IGMP over the years has had many versions. The major ones are 1, 2, and 3. There were some minor versions that never got ratified. But the original implementations are still IGMP version 1 and IGMP version 2. Version 1 was obviously the very, very original release, the first ratified release. And IGMP version 2 added a few new features to IGMPv1. For the most part, they are same. So IGMP version 1, like we discussed, it had mechanisms for receivers to join a group, but it did not have, basically when you wanted to leave the group, you just left it silently. So a receiver would just stop sending any more multicast IGMP messages, and the router kind of just had to assume that everybody had just left the group. And it's sad now, there is nothing to send. But with IGMP version 2, there was an actual mechanism that was introduced that allows the receivers to leave a certain group and inform the router about leaving that group. So in version 1, the router could just keep forwarding the unwanted multicast packets. So think of the last receivers now just left silently. It's gone. And the router doesn't know this, so it basically keeps forwarding unwanted multicast packets. The other thing that IGMP version 2 added was an election process for a querier. So we'll talk about what querier actually is. But querier is the router that will do sort of a health check on the receivers. It'll periodically check which receivers are still interested in which receiver groups. And if there are two routers on a segment, then you don't want to do double duty, so they elect one router out of the two to perform these polling duties. In version 1, the multicast routing protocol was responsible. So whatever was the designated router of the multicast routing protocol, that also became the designated querier. But with version 2, with different multicast routing protocols now, it could be different IGMP queriers, and that just wasn't good enough. So version 2 adds this support for a querier election. Again, we'll discuss the differences in a lot of detail, but that's basically the gist of it. That's the differences between version 1 and version 2. That brings us to the actual messages that carry all of this information in IGMP version 1 and version 2, what they actually do, and their basic descriptions. Now, each one of these is covered in a lot more detail as we come up, but think of this as just a summarization of it. The very first message here is what is called a membership report. Now, the informal name for this is actually a little bit more descriptive. It is also, you would often see it called an IGMP join. This is how the receivers actually signal their interest in a multicast group to the multicast routers. So if there was one message that you couldn't do without, this would be that message. It would be the IGMP membership report, or also called the IGMP join. The second message is a leave group message. This is how the receivers now inform. Now, this is specific to multicast version 2 only. This was the added functionality that differs IGMP version 2 from IGMP version 1. And this is how the receivers inform the multicast routers when they are no longer interested in a group. So if they no longer want multicast stream coming from to a group, they can sever themselves from that group by sending a leave group message, and this is a specific message to V2. The last message here is the membership query message. Now, this is how the multicast routers confirm continued interest of receivers in a multicast group. And we'll see how this actually fits in. But usually there are two types of queries. And all you're trying to find out is, do receivers still want to keep receiving traffic from a group? And remember, back in the days of version 1, there was no leave group message. And that sort of necessitated this anyway. But even otherwise, suppose a multicast receiver just dies in its tracks. It could never send the leave group message and it just turns off without sending anything. How would you ever know that they still need, or that group doesn't really need to be sent there anymore? That's where the multicast membership query would help us. There can be two forms of queries. The first one that is supported in both version 1 and version 2 is the general query. The general query is a periodic message, and it's basically to update the status of all multicast groups. So all of the active multicast groups on a router, the general query would be sent periodically to essentially update the status. Should I keep forwarding packets on that MC group, or should I not forward any more packets? The second one, and this is specific to version 2, and it has to do with that leave group message. It's a group-specific query. This is an event-driven query. Again, the underlying functionality or the underlying reason for it is the same. It needs to update the status. But in this case, it is about particular multicast groups. And it is also, like I said, event-driven. It's not periodic. And the event that drives this is a host leaving a group, or host sending a leave group message. Now, think about it this way. When a host sends a leave group message, essentially what the router is confirming with a group-specific query is all of the other receivers that might be listening to that group or might have registered up to the source. It is essentially now polling them, hey, it looks like one of the receivers wants to leave. Is it true for everybody, or should I still keep sending messages on this particular group? But again, we're going to talk about every single one of these in a lot more detail. And we will begin with the IGMP membership report. So like I said, this is the crux of it all. This is what we're called IGMP joins informally. And we're calling them version 1 and version 2 joins, but essentially it is a message that asks for the reception of a group. So this is how receivers actually join multicast groups. And who they are signaling, so this is a signaling message, right? You're sending some sort of multicast signaling up. And who is being signaled? It is actually the multicast router on the local segment that is being signaled. So think back to that little topology that we drew where we were getting in IGMP messages and turning them into multicast routing protocol messages. That's the multicast router on the local segment. We also defined it as LHR, or last hop router. Now, the multicast router listens to all multicast traffic. It has essentially subscribed itself to the entire class D. It listens to every single one of those groups. Now, from this point on, calling it a membership report every single time is sort of cumbersome. At the same time, I don't really want to call it a join. So a good middle usually is to call it either an IGMP report or just a report. So every time I say a report or IGMP report, that essentially means an IGMP membership report or an IGMP join. You will see good reason why I don't really want to call it a join. There is another join concept that we will deal with in advanced lectures, and it's good to just get your basics squared away and call it what it is, which is an IGMP membership report. Now, ultimately, it is carried in an IP packet. We discussed this before. IGMP is IP protocol number 2. So it ultimately has to reside in an IP packet. That IP packet would also have a source IP. This one's actually pretty easy. This is the host's configured IP. The IP that is on the interface of the host, that is just used to populate the source IP field. The destination IP field is a little bit more interesting. This actually is the group's multicast address. Now, which group? Well, the group that you want to join. So for example, if you want to join 239.1.2.3, then that would be the message that is used as a destination. So we will see why this actually is done this way, but for now, know that the destination IP is multicast, and it is also the actual group that you want to join, that you multicasted on. Another interesting thing here is if you look at the IP options of this packet, you would see the router alert option. So in addition to being a TTL of 1, there's also the router alert option that makes sure that any router receiving this message will actually process it, no matter what the TTL is. So that's what the router alert option essentially does. And it does it for the host as well. The multicast router, so who is going to accept these packets, right? So the multicast router will accept this packet. And there are two reasons for it. It is listening to all multicast traffic, number one. And it's also TTL of 1. So essentially it receives it and accepts it. The multicast router will further process this message, and that's mostly again because of the TTL of 1 and also the router alert option. So both of those things cause the packet to be actually processed by the multicast router. Let's look at the packet structure real quickly, and we are not going over the actual mechanisms just yet, but we're just looking at the packet structure. It's a very simple structure, and you will see that this packet structure is used across the field for the reports and the leave group and also the queries. It has a type, and the type essentially tells which sort of message it is. Is it a report? Is it a leave group? Is it a query? Whether it be general or specific. Now, 16 is the membership report for version 2. And you would also see 12 used because IGMP version 1 is version 2 rather is backwards compatible with version 1. So you may see the type as 12 also, and that essentially just signifies that it is a version 1 join. The maximum response time here is not actually used. This is an unpopulated field. We'll actually see it being used for other purposes later on, specifically with the queries, but for right now, there's nothing there. The checksum is the checksum. Basically, it verifies the packet. And finally, so there was an actual group, so you can identify the group here in the destination IP. But again, inside the packet, the group is once more contained in here. So this same group would also populate this last field of the membership report. So at two places, you can actually find that particular address. And these should really be consistent. There's not much reason for them not to be consistent. Now we'll discuss what this message actually does a little bit later, but I want to go over all of the messages before we start getting into the actual processing of this. The next message here is the IGMP leave group message. And this is particular to IGMP version 2. It's not present in IGMP version 1. And this is how the hosts actually inform the router or routers rather, that they want to leave multicast groups. So they no longer are interested on the traffic. Once again, the router being signaled is the LHR. So that bears repeating. The LHR is the router, the last hop router is the one you're trying to signal. And it is not used in IGMP version 1. IGMP version 1 uses what is called a silent leave. You just sort of disappear into the ether, and the messages keep going somewhere, but they're not coming to you anymore. You're not listening to that group, or at least you're not processing those packets anymore. Once again, it is an IP packet, IP protocol version 2. And once again, the source IP is the host configured IP. That really hasn't changed. Now, the destination IP for the leave group is more well defined. It's actually 224.0.0.2. This is a special IP, and it is known as the All Routers Multicast. So All Routers Multicast, as the name defines, all of the routers are tuned to it. They process packets that arrive on it. This particular message, the leave group message, will not be heard by anybody other than the routers, or it shouldn't be in a well-functioning network. Once again, there is the router alert option so that the router knows to process this packet. Now, who accepts this and who processes it and why? So the multicast router will accept this packet because any multicast router must accept the All Routers Multicast. So that's very simple. And the multicast router processes this packet because of the router alert option. Also, the TTL it's tuned to a 1. The packet structure remains exactly the same. So like I said, you would see this packet structure over and over again. The only thing that is different is the type. So the type is a new type. It's only applicable in version 2, so there are not two different types. There's just one type, and that is OX17. So OX17 tells the router that it's a leave group message. Once again, the max response time is not used. Once again, the checksum is the checksum. Now, the group address here is more important. So if you wanted to leave the same group, you would actually use that 239.1.2.3 address here. So that's the group now that the host is trying to leave. And that's the leave group message. We'll go into the actual mechanisms of it, but this is the description of it. The next message and the last one here is the IGMP membership query. This is literally like that Lionel Richie song. It's hello. It's anybody out there, anybody interested in all of these groups. So multicast routers have those multicast states. These are soft states, and you're using a lot of processing power to actually keep those states alive. And that's why it's imperative that you do not send unnecessary traffic onto the network. So this is how the multicast routers, they will keep an updated information tally on their IGMP states, or the traffic that they actually need to forward on the segment. Now this is sent to all the multicast hosts on the segment. All multicast hosts must receive this message, and all of them must also process it. So sent from the router and sent down to all of the multicast hosts. Now, once you receive this message, so once the host received this message, the idea here is that one host per group. So if there are many groups, one host at least per group must respond. So must respond for the group, for the whole group to remain active. So if nobody responds at all, the group can actually go passive. So it's imperative that the group remain active as long as there are interested receivers. And for that, one host must respond. We'll see how they make sure that not more than one, or not everybody's responding. One suffices. One makes sure that the router can still keep the state, but at least one host per group must respond. We'll also see what that response actually is. Going into the actual IP packet of this time the message is not coming from a host, right? So the message is actually coming from a router, and more importantly and specifically, it's actually coming from what is called the designated querier. So it's coming from the designated querier. It's basically one of the multicast routers out of many on the segment that has been chosen for these duties, and it uses its interface IP for the source IP. Now the destination IP, remember we talked about two different queries, whether it's a periodic general query or is it an event-driven group-specific query. Depending on that, the destination IP is different. Now, a general query, you're basically doing a health check on all of the devices that are, or all of the multicast receivers, and you want to see if they're still interested in groups. So it's important that everybody sort of receives this, right? So this is sent to 224.0.0.1. Once again, this is a special IP, and this is known as the all systems multicast IP. So every single multicast, receiver, host, router, switch, anybody, they should all process this message. So this is the general query message. Now, the group specific query is actually a lot more limited. So you're inquiring about the status of a particular group. So wouldn't it make sense to only send it to the people who are supposed to be listening to that group? Well, it does to me. So in this case, the multicast IP, so once again, the destination is multicast, and the IP is the actual group that is being queried. So suppose once we receive a leave group message for 239.1.2.3, then this would be the IP that would be used as the destination IP in a group specific query. And for the last time, again, there is a router alert option built in because you don't want people to, or you don't want multicast hosts or other routers to drop this message. You actually want them to process it. So there's a router alert option. This time in the packet structure, we are introduced to a brand new field. So there is the type that has been there in literally every one of these. The type now is OX11. The same message essentially is used. So general queries and group specific queries both use the same type. And general queries existed in version 1. So this is both for version 1 and version 2. There's not a divergence there. I'll skip some of this to go to the group address. Now the group address may be left empty or 0.0.0.0 for a general query because we just want to query everybody. Or it may be something like 239.1.2.3 for group specific queries. So it's going to depend what that group address is. But by this time, you should be more familiar with it. But the field that is more important here is actually the max response time. This time the field is actually populated. It will be populated with something finite. Think of in the number in tens of seconds usually. So if this field says, I don't know, 100. So in tens of seconds, that actually equates to about 10 seconds. And what this field is saying, so remember, the query goes out and you're expecting a response, right? So this respond is a response. This is how much time you have to get that response back to the router before it takes some drastic action, as in stop sending multicast packets to that group. So this max response time is now very important in a multicast group-specific query. Again, we'll go over the mechanisms of it, but for right now, this is what the packet looks like. Now that we have actually discussed all of the messages that IGMP version 1 and version 2 use, now it's time to actually see how they are used to provide all of the mechanisms of IGMP version 1 and version 2. The very first one, this is, call it the base scenario. This is a brand new receiver that is joining a new group. Again, apart from this type here, so if you look at the actual type, apart from the type, there is nothing different about this message between IGMP version 1 and version 2. It remains exactly the same. The scenario is this. A receiver wants to join a group. Again, where it got the group information, probably from an application layer. And it sends a membership report. If you remember the membership report slide from like 3-4 slides ago, the actual message is multicasted on the group IP address. So the destination IP is the group IP address. Now, there is something called the join latency. The join latency essentially means how long does it take for a router to start receiving traffic once it has the intent to join the group. So that's the latency. This message must be unsolicited. That means it must be unprovoked. That means you should not wait for anything just to send this message out. And the reason for that is you want to reduce that join latency. So you don't really want to wait. Once you've decided that you need traffic for a group, you don't really want to wait. And to eliminate this join latency, you just send this message. And it's completely unsolicited, unprovoked. Now the recipients here are all of the multicast routers. So there are two sets of recipients. So there are multicast routers, and that's because they're listening to all multicast messages, including the group IP where this was sent. So multicast routers will receive it, but the other group members, the other members who already probably exist on that group. So suppose you join 239.1.2.3, and there were 5 other members on that group. Because you're multicasting this message to that group, that means every single receiver on that group will also receive this message. So they get this because they're listening to that multicast group. They're interested receivers. They both perform separate set of actions. So these actions are now important. So let's see. First of all, let's get a brand new router. Or brand new receiver. Let's say receiver 2 here wants to join a group. We'll just call the group G. It's easier to say that. It's easier for me to write that. 2 will then multicast a report with the group address G contained in here, and it'll multicast it on G. So essentially what happens, suppose, let's identify all of the routers that are listening to G in blue. So these are already the interested receivers in G. G is also blue, and G is also blue. So they are all listening to it. 2 is going to multicast a packet out. Now, if the switch at this layer 2 is intelligent, like we discussed earlier, it'll send that packet at least to all of the members of the group. So it will send it over to number 4 here. And it'll also send this over to number 1 here. But more importantly, it will send it up to both of the routers. So both of the routers actually receive this message because they listen to everything. So from the group members, what can happen, so we will get more into this, there is something called pending reports. And these pending reports are in response to the membership queries. So the queries that the router is sending. Anyway, the point here is either these members, those actual members, take no action at all, or they cancel any pending reports for the group only. So only for that G group, the blue group, they will cancel any pending reports because basically somebody else from the group updated the status. And like I said, as long as one person from the group updates that status, the group is good to go from a router point of view. And that's all that's needed, right? But for the multicast routers here, it's much more important. There's more processing here that happens. Now, if that state hasn't existed before, it's a brand new group. Suppose 1 and 4 were not joined to it. Then the multicast router will create new state for that group. Now that new state means that it'll create an actual IGMP state, and these two interfaces would then be added to the oil. But more than that, it also signals that oil up to the multicast routing protocol. So whatever multicast routing protocol it's running, that essentially now gets kickstarted for that group. So create new state if none had existed, and thereby you reduce the join latency as we had talked about. So now you can start sending to that group almost immediately. In case the group already existed, so the group was previously present, there were other receivers listening to that particular group, then what the multicast router is going to do is refresh the timers for the current state. Now each state will have a timer. We'll discuss that in, I would say, 2 slides or so. but there is a timer that you expire for each state. This particular action essentially just refreshes that timer. And that is all there is for a brand new member joining a group. This is an unsolicited join that is sent up to the routers and also to all of the other receivers on that particular subnet. The second mechanism here is the mechanism of that periodic general queries and the responses to those general queries. So, like I discussed before on the last slide, every IGMP state, and now this is every IGMP state for each group, every single group, on the router has a timer associated with it. So there is a timer that is counted down. And if the timer completely expires without getting refreshed, then the state goes inactive. So the state just kind of goes away. So in order to keep the state active, those timers must be refreshed periodically. And the general queries basically kickstart the whole process of this refresh. So in order to ensure that, why would you need to keep the state active? Because there are interested receivers still present for that group. So essentially what you're asking is all of the interested receivers on all of the groups to kickstart a process and send those reports up to refresh the active state. Because of this reason, as we discussed before, because every single multicast recipient must process this message, it is actually sent on 224.0.0.1 or all systems multicast IP. You want to make sure that if this report comes down from this router or the designated courier, then it is sent to every single multicast receiver. Because you don't want to lose out a group, and this is the most scalable way of doing that. So once again, it bears repeating, every single multicast device. So when I say IP device, I mean multicast device. And most IP devices are multicast devices. Now the actions are more interesting. For the hosts, suppose there was basically a polling and a reporting. So query and a report relationship. So as soon as you got the query, then your response was to immediately send a report. Think of even in our small network what would happen. You may get a couple of reports from here for the two groups here. You may get a couple from here. You may get 3 or 4 from here. You may get 10 from here, depending on how many groups you're subscribed to. Think of the processing on this poor guy now. So this is not scalable at all. So if there was immediate sending off that report, then that would not be sufficient. And for that, or scalable. For that reason, like I discussed before, there is this maximum response time built into the packet. So you populate it with something, the default I believe is 10 seconds, but you can make that bigger or smaller. Now the action on the hosts first, because the hosts are going to respond, they start a random timer and they make sure that the random timer is less than the maximum response time. So you don't want to take longer than the maximum response time to respond, but you start a random timer and you start it per active group because you want to make sure that whatever groups are active on your interface, they should get refreshed in this go around. Now this timer starts counting down. So it's counting down from somewhere less than maximum response time. So somewhere between 0 and 10. Suppose it was a nice round number 8. And it is counting down from 8. So it's going to 7, it's going to 6, 5, 4, 3, 2, 1. If the timer is allowed to expire all the way, it goes 0. Then the host sends an IGMP report for each of the groups that the timer expired for. So you would send those reports for every single one of the groups that the timer expired on. However, suppose, so let's look at the scenario again, and let's suppose the query is for the group G once again, our favorite group. And who was subscribed to G? I think it was this guy here, this fourth guy here, and the first guy here. Now all of them will start a timer. So depending on the maximum response time, the random property of the timer is very important. So suppose the timers that they set were 5, and how about 3, and how about 8 for this last group. So now they're all counting down from the same exact time the report was received. But who is going to expire their timer first? If you look at it, it's going to be this guy here. He is going to expire that 3-second timer at the end of 3 seconds, while there are still 2 seconds left here, and while there are still, 5 seconds left here. So once that timer expires, it will send up a report. And that report, remember that it was multicasted to the address G. That means that report would be heard by the other members of the group, which are 1 and 4 here. And now that they've received a report, they can go ahead and they can cancel their timer. They can cancel their timer and their report, basically. What you're canceling is the timer and also the report. You're not going to send the report. Why? Because another IGMP report for the group was heard. So you don't really need to inundate the router. It's a single interface. And as long as there is a single receiver, the router is going to send the multicast stream down. So that means the host doesn't have to update this IGMP report or send this IGMP report. Now for the multicast routers, remember all of the multicast routers, they are also going to receive this particular query. The general queries are received by all of the multicast routers on the segment. So this guy, suppose the first one was designated querier and the second one is just a router. So R is going to receive a message from DQ, and as long as DQ is sending packets and it has, I believe, a lower IP, I haven't seen that RFC in a long time, so I believe it's the lower IP. As long as DQ has the lower IP, it by default wins that querier election and it keeps playing the job of a designated querier. So one out of these two routers or one out of many routers is going to be a querier, and they basically rely on these periodic general queries to perform that election. So they hear each other, they have each other's data, and the other receivers or the other routers, essentially, they just keep quiet. As long as they hear better messages, it's sort of like spanning tree. They don't bother sending queries. They know that somebody is handling the queries. And they also refresh their states when a report is received. So in case the DQ does go down or in case the multicast traffic is coming a different way. So if the multicast traffic actually ends up coming to this router, then this router needs to forward it out onto the segment. They also need to keep the state active, and they'll basically use the reception of the report, which is sent by the host, to keep that state fresh and keep activating that state and keep pushing it up to the multicast routing protocol. So now, finally, a receiver leaves a new group, right? So receiver leaves a group. A receiver on a LAN that needs to leave a group, it just needs to inform the routers, right? So it doesn't really need to inform anybody else. All it wants to do is that the routers should now delete that particular state. They shouldn't send to that state anymore, not on this guy's behalf, but the other people, other hosts may still be listening to that group. So once again, just like there was join latency, there is also something called leave latency, and that means a host has left, but the router still keeps sending multicast packets on the group. That is leave latency. So this message has to be unsolicited. So the application layer says don't join the group or unjoin the group. The host complies and sends an unsolicited message, and that reduces that leave latency. As should be a common theme already, anything that needs to be heard by all of the multicast routers, that needs to be sent to this 224.0.0.2 address. So that's where the leave message is sent. The recipients this time are only the multicast routers. I don't need to state the reason, we already know. And these are the actions that it performs. So now it will send that group-specific query. So it will send a query for a certain group that is being left. It is not a general query. So remember we talked about an event-driven query? Well, the event is this leave group message. So the leave group message is the event, and the response is this group-specific query. And essentially what you're asking is if other members are still interested in that group, they still exist in that group, and those members should then respond, we'll talk about it in an upcoming slide, but they should respond with a membership report, otherwise the group would just be deleted. And this would be deleted from the multicast router. So those routers are essentially being told, hey, there is a person who wants to leave. Are you guys still interested, or do you want me to just get rid of this group? So like we talked before, the group-specific query is that event-driven query that is coming from that leave message. Again, the type of it does not really change. The type is OX11. The type is OX11. There is also a maximum response time, and there is a group address for the group that the group-specific query is for. Now, this is only sent if the last host to leave. So depending on who sent that last report on the general query side. So if a general query goes out, so let's talk about a general query first. If a general query goes out to all of these three routers, only one of them responds. Remember, there is that random time and only one of them responds. So suppose in this particular case, the response came from router 1. Now, how the group-specific query would work really depends on who sent the group leave message. Suppose, so the router now has updated the state using the IP of 1. So as much as it knows, 1 is the only interested receiver that is absolutely sure of, because the router received a report from that particular host. If you receive a leave message, so let's call this blue the leave message, from one of the other hosts, it is not coming from what is called the last reporter. So the last reporter was 1, but the message now is coming from 3. That means the router already knows that, hey, 1 is still interested in this. They haven't sent me a leave group message, so 1 must still be interested. And in that case, they would not send this group-specific query. So the group-specific query would only be sent if the last reporter, so the only host is the last reporter, because there's just one person that the router is aware of, and the host to leave should not be that particular host. So you would only send the group-specific query if this 1 left. You would not send that group-specific query for any of the other hosts leaving that group. So we already discussed how these queries are event-driven, and they are multicasted on the group address as well. So they are not sent to the all systems multicast. They are actually sent only to the group IP address, which would be G in this case, and that G is also contained in here. The recipients, well, it should be simple enough. If the destination IP is G, then all of the members subscribe to G. They would then become the intended recipients. And what happens here is pretty much similar to what happens for a general query. The host starts a random timer, less than max response time. And this would not be, actually it would not be per active group. It would only be for that G. So it would only be for that G. Timer expires, send an IGMP report. If you hear another IGMP report, cancel the timer. So we went through the mechanics of it in general query discussion, but this is essentially what's happening. You need one report to go up for that particular group. Multicast routers, however, do not really use group-specific queries. They don't use it for election purposes or anything else. They would rather be interested in that last report. So if they can refresh that group or not, that is what they are interested in. So that brings us to the end of this lecture. In this lecture, we discussed Internet Group Messaging Protocol. Internet Group Membership Protocol, IGMP. We discussed version 2 and version 1. We discussed the actual mechanics of it. We discussed the packet formats. And we discussed how this multicast network is being signaled from the very get-go. So this is literally the very start of multicast. And this is how the receivers actually signal their intent. I hope you have enjoyed this lecture.